Welcome everyone. In this video I'm going to show you a neat little upgrade for these miniature DC motors. So these motors are typically equipped with some sort of gearbox. For example, this specific motor comes with a gearbox which has a right angle output shaft. So you can see that the motor's gear or the first gear on the motor shaft is right there. It's a worm gear, and then there are several other gears inside the gearbox, and then the output shaft is perpendicular to the motor's shaft. And then this specific model or module comes without any kind of encoders, so this cannot be used for any kind of positioning because obviously we don't know anything about the motor's movement. But there are other models, for example this one. This has a straight gearbox, as you can see. So essentially the main output shaft here is just the extension of the motor's shaft. There is nothing extraordinary about that. But here at the back side, once my phone focuses, you can see that there is a magnetic encoder. And in principle these are just two Hall sensors. And then inside this disc there are several magnets basically, and then as the magnets or the magnetic parts pass by these two sensors, then the circuit generates a square wave output on the output pins, as you can see, C1, C2, and then they can be processed as usual using a microcontroller, for example an Arduino. And then based on the shaft, how it rotates and so on, and how many pulses are counted, we can kind of get an information about the displacement of the main shaft here. So for example, these kind of encoders, they can come with mainly two different configurations. One is 3 pulses per revolution, so 3 ppr, or 7 ppr, so 7 pulses per revolution, but there are other models as well. So that means that if you do a full turn of the shaft, then you will detect 7 or 3 pulses, depending on what kind of disc you have here. And then that is just a full turn on the motor's shaft, but what if we want to know how many pulses it takes to get a full turn on the main shaft? And then that is simply just a multiplication factor provided by the gear ratio of the gearbox here. So for example, if this is a 1:50 gearbox, then that means that the motor's shaft has to rotate 50 times to get one full turn on this shaft. So if this is a 7 ppr encoder disc, then 7 times 50 pulses are needed to be registered in order to think that we are at, we did one full turn on this shaft, on the main shaft. But there are several problems with this kind of motor or gearbox or both, is that there is a lot of backlash and slack in the system. So one of the problems is that I can rotate this shaft a little bit, so that gives some uncertainty. But also when the motor is running and it is stopped, then there is still some inertia in the gearbox and in the whole mechanical system. And another problem can be that due to the, let's call it, flexibility inside the system, or due to slipping of the gears, it can be that the shaft here moves more than we think based on the number of clicks or pulses from the encoder. And that's a big problem, because then this shaft, the motor's shaft, and this shaft, which is the gearbox's shaft, are not synchronized. So that's not so nice, because then it's hard to use this motor for positioning in an easy way. So the solution is here in my hands, and this is nothing else than just another version or another piece of this motor with a 3D printed bracket around it, and then here we have a sensor, which is this AS5600 magnetic encoder chip. And this is an absolute encoder between 0 and 360 degrees. So that means that it can detect the position of a magnet placed over this chip between 0 and 360 degrees on an absolute scale, but of course with the help of some software it can detect any kind of position wherever you move with the magnet. So if you do multiple turns of your shaft, then of course this can account for it, and so on. And I have a very popular video on this chip. It's right there in the corner, so please check it if you want to understand how this works. But now we should focus on this. So what we have here is maybe easier to understand if I disassemble this. So I just removed this encoder. So you can see that this is the same sensor. And then here, this is the most important thing, is you can see that there is a tiny magnet there, and that is placed on the main shaft or on the back of the main shaft. So basically it detects anything, any rotations which are happening on this part, which is the final part of the, let's say, gear box. So that's very good. So you can see here on the picture that at the bottom we have the magnet, and then here we have the main shaft, and it's sitting on the same shaft. And I try to do my best to place this at the center, but since this is a 1 millimeter diameter and 1 millimeter high or tall magnet, it is not the easiest way to do so, but you can see that the magnet is placed there. So then this bracket is just designed carefully to accommodate this module and to provide sufficient distance between the magnet, there you can see it, and the sensor. So that's what we have here. And I also tried to align the holes in a way that when I screw in the holes, then the center of the sensor is exactly over the center of the magnet. That is very important to have a very symmetrical arrangement or alignment, because otherwise the magnetic readings won't be too precise. So let me screw this back, and then we do a little demonstration of this thing, how it works and so on. So I assembled a very simple demonstration kit under this disk, which is divided into 8 zones. We have the motor, so this guy with the bracket and the encoder, and this is a DRV8833 2-channel DC motor driver. It can be adjusted with PWM. We have a rotary encoder because we will be defining a target position in angle or degrees, and then the motor should move there. We have a display with I2C. It will show the target position plus the actual position of the encoder, and we have an Arduino which will drive everything. And I kind of recycled my old PWM-PID code. In the past I used this motor and this shaft with an encoder at the back, and I already showed some kind of demonstration with the title something like N20 geared motor with encoder and PID, so check it, I put it there in the corner. So I kind of recycled that code and applied it on this specific scenario. So I replaced the encoder part and made it work with this encoder instead, but the principles are the same. So yeah, we have a 5-volt power supply here, and then I have a power supply for the Arduino. So I plug in the Arduino and then we see how we proceed. So everything is powered. The display is not very visible, but I will try to make it more visible when I edit the video. But you have to trust me on this. So what we see here is actually an interesting thing, is that the value is fluctuating. And first of all, many people miss this thing that when you use this board, or when you use this chip in general, there's this direction pin, and that has to be tied to the ground. If you leave it floating, then you will have even larger fluctuations. But what you see here is that the value is fluctuating with plus minus 0.088 degrees. And what that means is that actually one bit is flipping up and down, because this encoder, this guy, has a resolution of 12 bits. So that divides the whole observable level into 4095 levels or steps. And if you divide 360, so the full turn here, with 4095, guess what? You get 0.088. So that means that one bit, so LSB, the value of the LSB is basically 0.088 degrees. So the LSB is probably uncertain here, and that's why the angle is jumping up and down. So that's what we see there. But now let's say we are at 0 degrees, and the target is also at 0. But I haven't yet powered on the module, so I do that right now. And now I decide to do something with the encoder. So I just turn it, and I will try to move to, let's say, 180 degrees first. So now the target position is at 180. So when I press in the encoder, then this pin should move down. This is just a zip tie. So the movement is not exactly precise, as you will see, because this is off-centered as it rotates. But let's see what happens. And you can see that we did 180 degrees. So the marking is a bit behind the pin here, or the needle, because of course the needle up here was a bit ahead of the tick here. I can show it. So let's return back to 0. So then this should rotate backwards. And then you can see that the needle stopped a bit before touching the tick there, or the marking. And that is just, yeah, nothing very strange. So now let's go to 270, so that should be somewhere here. And now we stopped at 269.9 something. So that's that. And I can move back to, let's say, 90 degrees. And then the needle should end up somewhere here. And it's there. And back to 270. And it's there. So you can see that this moves quite easily. And as I said, there is nothing extraordinary behind this. It's a very simple PID algorithm, which relies on the position information provided by the encoder, which is attached here at the back of the shaft. And then there's a magnet on the back of the shaft, so the encoder is somewhere here. And that's that. And that eliminates all the errors which could happen inside the gearbox. which is very nice, especially with these motors. So now I think this was enough demonstration. If you want to see the circuit drawing and the schematics, then go to my website, because that drawing is there. But I quickly want to explain the code and how it works, so you can understand the principles behind it, and you can also apply it on your projects. So let's move to my computer. Okay, so we are here with the code, and once again, please check the related videos carefully, because most of the code is borrowed from those two videos. One is the AS5600 video, and the other is where I show how to drive a similar geared DC motor with a magnetic encoder using PID. So this is just a combination of those two plus a little polishing. So I will do kind of a speed run here, because it would take a lot of time to explain once again everything, and actually I have already done that. So we have I2C display, the OLED display, so we need these relevant stuff for them. So just the libraries and just some pin definitions, and then we create the instance. And then here we have magnet related stuff. Again, this is in the video that I told you to check. So yeah, we just need these relevant parameters, variables, just to have everything done. An extra variable here is the magnetic encoder time, because I was playing around with the reading period of the encoder, because I was thinking that I could have unstable readings because I tried to pull the sensor too quickly or too often, so that might have a detrimental effect on the accuracy. So I try to see that, and I will show you that I was trying to do something. And then this is the relevant to the other video where I show the PWM and the PID control. So once again, we just have a PWM value and then two direction pins because of the motor driver. You have two input pins, and based on how they are driven, high or low, they will drive the motor in the positive or the negative direction. Or if the high pin is driven by a PWM signal, then based on the magnitude of the PWM signal, the motor will go with a certain speed, of course proportionally to the PWM signal and its magnitude. And then we have a rotary encoder. So here I just randomly assign pins. Of course, one of these two pins have to be interrupt pins. Actually, in this case, with this specific microcontroller, both of them are on an encoder pin, but I use only the two as a real encoder pin. So that's that. And then this is one of our most important parameters. This is the set point, the target position. So the PID will try to reach this value. And then we have some other values, which is, for example, the motor position, and that is the position information expressed in degrees unit, read by the AS5600 encoder. And then here I have some parameters. I was playing around with some PID parameters. You could see how the motor behaves. It is not really hunting for the position, it goes directly there. Which is achieved by these three P, I, and D parameters. Then again, a bunch of PID related parameters which are used in the calculation, how the three P, I, and D parameters are calculated, and then just some other parameters or variables used for the rotary encoder to determine the direction of it. And then we arrived in the setup. I was using the serial for some debugging, so of course I need the serial port, and then I have the I2C as well, and I defined a higher clock speed for the I2C here with this definition here. And first of all, before starting everything, the code has to check for the presence of the magnet. And actually, if there would be something wrong with the magnet, for example, it's too weak, or the magnetic strength or the magnetic field strength is too weak, then the code hangs here until you fix it. But you could see that in my demonstration, the code booted up properly and the magnet was close enough to the encoder. And then we do a reading of the raw angle. So basically we just read the actual current position or the startup position of the encoder. And then I pass that reading, which is this, to the start angle. And then I run this function. I will show them how they work to actually tear the reading. So where you boot up the system, regardless of the magnet's position, that angle will be considered as the zero angle. This is just relevant for my demonstration right here. You don't actually need this if you have other kind of applications, but this is how I do it in this demonstration. And then I just set up the encoder related stuff. Then I also define the two motor driving pins as outputs. I read the rotor encoder, and then I set up the OLED display basically. And then I print the permanent items on the display with this function, which is just printing the text part on the display once, and it is left as is. And then the refresh display actually prints the numerical values on the display. So what happens in the loop is that first we read the position of the magnet, and here is this line which I now commented out, which regulates the sampling period of the encoder, but I just wrote this, so actually it's checking as quick as possible. I might not need this if I just use this. So we read the angle, then we correct it according to our position, and then we check the quadrant, so that will actually finalize the total displacement in terms of rotations. And once we know that, we know our position, then we can calculate the PID parameters, and based on the PID parameters we can drive the motor. So give out some command to the motor driver circuit. And then we also pull the rotary button, so if we press the button, this function will pick it up, and after that we refresh the display. And then you can see that only these functions are in the loop, so this goes over and over. So we continuously read the position and drive the motor accordingly, and then refresh the display. So that's all. So how we drive the motor is that based on the control signal, we set up a direction. So if the control signal is negative, then the motor direction will be also considered as negative. If it's positive, then the driver signal or the direction signal is also positive. And then here I do a little bit risky thing, that if the value, so if it's not positive or negative, and you can see that there is no equal sign here, so either less or greater than, but never equal at the same time. So then of course the else would be when the case is 0, and that would stop the motor because the motor direction is 0. And this might be a bad practice. I even wrote it here because it could be that there is some inertia, as I mentioned it during the demonstration. So the motor actually overruns the 0 position, but the inertia still spins the axis. But for a moment, the error value can be 0, and maybe the code can catch it when it becomes 0. And that causes a big trouble because it shuts down the whole thing, and then the system still spins a bit. So then actually there will be a larger error. So actually that would be corrected within a few iterations, but it's just a bit, I don't know, feels weird to stop the motor, and then after a few loops the motor realizes that, hey, I went over or went under my position, so I have to drive again. So that could lead to, for example, hunting for the actual 0 position. So this might not be a good practice. That's what I'm trying to say here. So once we have the control signal, we have to cap it, because we only have an 8-bit PWM driver here in the Arduino. So it makes no sense to pass a larger than 255 value to it. And here I also do a bottom capping. So if the value would fall below 60, and this is purely empirical value, if you build your system, you have to experiment with this value, because below a certain PWM value, the driving power, current, voltage, whatever, could fall too low. So even though you have a certain PWM value, your motor will only emit some high frequency, high pitched sound, but it will not spin because of the friction, and all those things overpower the actual torque of the motor. So that would mean that actually some current would run through the motor's coil, but it would not go anywhere. So it could even overheat the motor. So what I concluded here is that if I drive with at least 60 as the PWM value, then the motor will find its target position at the end. And then this is another thing which I mentioned, that I put the error margin plus minus 2 degrees. So if we are within plus minus 2 degrees of the target position, then we can stop the motor. So PWM and motor direction is set to 0. So actually this will be performed when this becomes true. But let's start from here. So if the motor direction is this, then I turn on the motor by setting its or the motor driver by setting its standby pin to high, and then I write a corresponding PWM value to the direction pin 1, and I set the direction pin 2 to 0, so low basically. And these depend on the motor driver. This is applicable for the DRV8833 driver. And then if we have 1 as the motor direction, then we do the opposite as we did here with the direction pins. So the pin 1 is 0, pin 2 is PWM value. And then if we are in the else branch, then everything becomes 0 or low. So this shuts off the power from the motor driver, and then this just kills all the signals. And here, actually, since this is the last function that runs during the driving of the motor, I put these here. I maybe uncomment it just to make it more visible. So what this does is that it prints 4 values with space separation. So actually, you can use this serial plotter, and you can plot the things very nicely. When I finish with the code, I will show it how it works, and it's super cool. So I even keep this in the code now. And then how we calculate the PID, I'm not going to explain this because I explained this, and actually if you look at other YouTube videos, everyone will basically show this, because this is the basic textbook example of how to calculate PID parameters for your system. So I just show this to you. You can copy it and write it, and then that's all. And then we have the display permanent items. So these are the items which are never removed from the display, and it's just simply first line we print the text target, and in the third line we print the position text. So that's all. And then when we refresh the display, we only refresh it every 100 milliseconds if the values are changed. So basically that's that. The target value is printed with this rotary value variable, and it's put in the second line because the numbering starts from 0. So first we move the cursor to the beginning of the second line, and then we erase the line by printing spaces. We move the cursor back to the beginning of the second line, and we print the target value basically. And then we store the most recent value and reset the timer as well. And we do the same with the motor position, but we move to the 4th lines beginning, delete everything, and then we print the position. And I print 3 digits because why not? So that's that. And then how we handle the rotary encoder is the same. So we read within, this is an ISR, so an interrupt service routine. When this is triggered, then we read the CRK now value by performing a digital read. And then in this if condition, we do some other readings, and based on the outcome of basically the final result of these two if conditions, we'll either decrease or increase the value. And here I should do this. So you can see that the step size is 10 because I did not want to spin the rotary encoder forever. So one click will be 10 steps up or 10 steps down based on the direction. The button is checked by polling it. So in the loop we always read the rotary SW pin and store its result in this variable. And then if the value is 0 and if there hasn't been any button presses in the last second, then we go and pass the target position to the target position value basically. And this is actually in my opinion, it's a very simple software debouncing. So what this part does here is that it only allows this part to be performed if the elapsed time here is more than 1 second. So what this does is that, let's say we enter this part and then we pass the value, and then immediately after that we update the rotary time. So then if the function returns here, let's say just one iteration after that, then of course this time this difference will be very tiny, let's say 1 millisecond. But that is still smaller than 1000 milliseconds. And why this is good is because if you click a button or press a button or a switch or something similar, then it will bounce. That means that its output signal won't immediately jump to 0 or immediately jump up to high value, but it will fluctuate or bounce. And what this does is that after we just recorded the first transition to 0 basically here, we don't listen to the switch for 1 second. And within 1 second the bouncing will most definitely decay. So then we will be ready, or the code will be ready to listen to the next real switching or button press. So here we read the raw angle, and again check my AS5600 video. But what happens here, we read the first bit and then we wait until the response. So we pass the response to this variable, and then we read the next 4 bits, the remaining 4 bits that I explained in the beginning, and then we store it in the high byte. And then what we do is that we shift first, and it's shown here how it is shifted. So the high byte is shifted left by 8, and that is basically just shifting out. If you can see it here that since the high byte is stored in a word which is like 16 bits, then this shifted to the left by 8, so it becomes this, or yeah, this. And then we have to combine the two variables, which is done by the bitwise OR operation. And then here you can see how the two numbers are combined and what is the final result. And here we get the raw angle, which is just the reading between 0 and 4095. And that has to be multiplied by basically the LSB value of the angle. And that will give us the degree angle. That's all. And after we read this, we have to correct the angle. So basically from each degree angle we subtract the start angle, and then we do some correction, because it can be that it would become a negative value. So for example, the start angle was larger in the beginning than the degree angle, and then yeah, the angle would not be proper for our reading. So this correction is implemented, and then we check the quadrants, and that is just to determine the transition between one of these 4 sectors, so 1 to 2 or 2 to 1 or 1 to 4 or 4 to 1 and so on and so on. So these transitions will determine whether we went clockwise or counterclockwise. And actually some people suggested me that this can be optimized, but I just did not find the time to check how to do it. So this is still the unoptimized code, because people said that actually it's enough to check less than 4 quadrants. 2 is enough, but I will have to check it first. But yeah, based on the angle where we are, we just tell the code which quadrants we are sitting in. And after we know that, then based on the transitions, we know if the number of turns have to be increased or it has to be decreased. And then, based on the number of turns and the corrected angle, we can define the total position, let's call it, or total absolute position of the motor. So if it turned, let's say 2 turns, and we are sitting at the 0 angle exactly, then this is 0, this is 2, this is 360. So it is sitting at the 720 position, which is 2 turns equivalent in degrees angle. So that's that. And then finally we have to check the magnet's presence, and this is also from the data sheet. So all we do is that while the magnet status and bitwise end operation with 32 is not 32, we are checking. And this is the part where the code gets stuck. So the code gets stuck in the setup if the magnet is not present properly because of this condition. So we constantly send instructions to the AS5600 chip that we want to get the status of the magnet, this guy here. So we read it back after we send the instructions. And as long as this value does not become, or as long as this value doesn't help to fulfill this while criteria or condition, then the while iterates here over and over. Otherwise, it exits, so then the magnet is fine. And we can print the status, what was it? And you can look it up in this figure 21, what value is what. But I did a small summary here. What you should see: if the decimal number is this one, then the magnet is too close. If the decimal number is 23, then the magnet is too weak. And if it's 55, then the magnet is all right. So then that's what we are looking for. So that's that. So now let me do some demonstration, and let me show you how things work in the serial terminal. So what we can see here is that everything is at 0, because basically the target position and the motor position is at 0, therefore the error value is also 0 and the PWM is also 0. And what you can see is that there is a small jump here, and that is that 0.088 degrees up and down. So that is kind of normal. And now I'm turning the rotor encoder to some larger degrees. So I set it to 720, which is 2 full turns. So what you will see when I press the rotor encoder button is that the target position will jump to 720, the error value will also jump to that value, the PWM will probably jump to 255, and then the motor position will start to slowly approach the target position. And the larger the motor position becomes, the lower the error value will be, and then when we are really close to the let's say 0 error value, or when the motor position is really close to the target position, then the PWM value will also start to drop. So I press the button now and you can observe what is happening. So here is the target, and here is the motor position, and then here is the PWM and then the error. And you could see that now the PWM and the error is basically 0, and then the positions are close to each other, or basically they are identical, so then these two lines are the same. And then let's go back to 0. So I'm turning the encoder. So the target position is at 0. So now what will happen is that the target position becomes 0, the motor position stays up here, and then the error value will be again 720 in the beginning, PWM will be 255, and then they will change according to the status of the system. So let's start it. And that's that. And actually this is now 1.49 something. So it's a bit above 0. This is the motor position and this is the target here. But if you remember, I actually decided to have a tolerance, basically plus minus 2 degrees. And this is within 2 degrees. So therefore the motor is not moving anymore. And let's go towards the negative numbers, because of course we can do that. So minus 200 degrees just for fun. And now you can see that these two values are at minus 200 degrees. And then here is the error and the PWM as well. So and let's go back to, let's say, something large and positive. (810 degrees, just some random number. So you can see how the signals evolve. So this is the driving signal here, and now it's going down the red line because the motor has to stop. And you could see that it was almost constant for a while, and that was the capping of the bottom value, which is 60. So it did not go below 60, and then all of a sudden when we are at the target it drops to 0. And that's that. So I think this is the demonstration. If you want the code and want to copy paste it instead of typing it as I explained it, please consider supporting me on Patreon. I always share the code files there, so you can just download it. But also it's a good investment for you or for those who want to see similar projects in the future, that obviously the more money I can get, the more gadgets I can buy and the more time I can dedicate to these projects. But otherwise you can just follow the video and type in yourself. And also don't forget to visit my website. I wrote a small summary about this thing, so you can see what is happening there, and also the schematics can be found on my website. And also if you browse a little bit more, you can find the relevant parts too. So you can buy the same motor, the same encoder, and at the same time, if you are using my affiliate links, you can support me as well without paying anything, basically. So I hope that you found this video useful. I hope you learned something, and see you in the next video.